Imagine a material, a single entity, holding the keys to both electricity and magnetism. This isn't science fiction. This is the captivating world of multiferroics. These materials are a special breed. They possess more than one ferroic order. Think ferromagnetism, like your fridge magnets. Think ferroelectricity, the magic behind your computer's RAM. Now, you might be wondering, why all the fuss about these multiferroics? Well, their allure lies in their potential. They hold the key to revolutionizing technology as we know it. Imagine faster, smaller, and more efficient devices. That's the promise of multiferroics. The beauty of multiferroics lies in their versatility. They're like a Swiss Army knife of materials. They can be tailored to exhibit a unique blend of properties. This opens up a world of possibilities, from next-gen sensors to groundbreaking memory devices. The future of electronics might very well hinge on these remarkable materials. They represent a paradigm shift. It's about harnessing the synergy between electricity and magnetism, and we're just scratching the surface of their potential. Multiferroics are like orchestras. Each part contributes to a harmonious whole. First, ferroelectricity directs electric dipoles, storing information in capacitors. Ferromagnetism provides the rhythm of magnetic moments, essential for data storage. Ferroelasticity adds shape-shifting used in actuators and sensors. Now imagine a material that combines all these properties, a true multiferroic. It's like having a smartphone in the world of materials. Just as your smartphone seamlessly integrates communication, entertainment, and information access, a multiferroic can exhibit electric, magnetic, and elastic properties all in one package. This unique combination opens up a whole new world of possibilities. We can control magnetism with electricity and vice versa. This crosstalk between properties is what makes multiferroics so fascinating and potentially revolutionary. It's like having a superpower in the materials world, the ability to manipulate fundamental forces with unprecedented control. And as we delve deeper into this realm, we're discovering even more exciting possibilities. Now let's talk about the real magic trick of multiferroics, Magneto-Electric Coupling. Imagine electricity and magnetism doing a waltz, perfectly in sync. That's what's happening at the atomic level in these materials. It's a delicate dance where electric fields influence magnetic properties and vice versa. This coupling isn't just a scientific curiosity. It's the key to unlocking some incredible technological advancements. Think about it. We could control magnetic data storage with electric fields, making devices faster and more energy efficient. This interplay between electricity and magnetism is what makes multiferroics so exciting for researchers. It's like discovering a new fundamental interaction in the universe of materials. Think of a hybrid car. It seamlessly switches between gasoline and electric power, giving you the best of both worlds. That's the beauty of Magneto-Electric Coupling. It's like having a hybrid engine for material properties. We can use electric fields to flip magnetic bits, write data with lightning speed, and create novel memory devices. This control over magnetism at the flick of an electric switch is a game changer. On the flip side, we can also use magnetic fields to manipulate electric properties. This opens up possibilities for new types of sensors and actuators. Now let's meet one of the stars of the multiferroic world, Bismuth ferrite. This material is a rock star. It exhibits both ferroelectric and antiferromagnetic properties at room temperature. That's like finding a unicorn in the materials world. Bismuth ferrite is a hotbed for research. Scientists are exploring its potential in various applications, from high-density data storage to ultra-sensitive magnetic sensors. But bismuth ferrite is just one example. There's a whole universe of multiferroic materials out there, each with its unique properties and potential applications. The story of multiferroics isn't a new one. It's a tale that stretches back to the 1960s. Think of those early days as the Wild West of materials science. Researchers were just beginning to explore the strange and wonderful world of materials with multiple personalities. Back then, the concept of a material being both ferroelectric and ferromagnetic seemed like something out of science fiction. But a few intrepid researchers dared to dream. They knew that if they could find such a material, it would be like striking gold. The challenge was that these early multiferroics were rare and difficult to work with. They were like delicate flowers, beautiful but fragile, and their properties, while intriguing, were often too weak for practical applications. The real turning point came in the early 2000s. Suddenly, everyone was talking about multiferroics. Advances in materials synthesis allowed scientists to create higher quality samples. Chromium oxide emerged as an early star, exhibiting magneto-electric effects. The field of multiferroics is still young and evolving rapidly. Okay, folks, let's talk applications. Where can these multiferroics make a real difference? Well, picture this: a world with super-sensitive sensors, lightning-fast memory, and energy-efficient electronics. That's the promise of multiferroics. One of the most exciting areas is data storage. Imagine a computer that boots up instantly, stores information with unprecedented density, and uses a fraction of the energy. That's the potential of multiferroic memory. And it's not just about speed and efficiency. Multiferroics could revolutionize how we interact with the world around us. Imagine sensors that can detect minute changes in magnetic fields, enabling everything from earthquake prediction to brain-computer interfaces. Let's dive into the world of memory devices. Right now, our computers rely on things like RAM and hard drives. These are great, but multiferroics could blow them out of the water. We're talking about a new breed of memory called multiferroic random access memory, or MFM-RAM for short. It uses the magic of Magneto-Electric Coupling to store information. Instead of just using electric current like in RAM, MFM-RAM can write data using both electric and magnetic fields. This means faster switching, lower power consumption, and greater data density. Imagine a future where your phone could hold a lifetime of memories, all thanks to the power of multiferroics. Now, let's step into a future home, powered by the wonders of multiferroics. Imagine sensors so sensitive they can detect changes in your health just by being in the room. Multiferroic sensors could revolutionize healthcare, providing real-time monitoring and early detection of diseases. But it doesn't stop there. These sensors could also monitor your home's energy consumption, adjusting appliances and systems for maximum efficiency. They could even enhance security systems, detecting intrusions with pinpoint accuracy. And let's not forget about entertainment. Imagine ultra-high-definition displays and speakers that use multiferroic materials to create incredibly realistic audio and visual experiences. The possibilities are truly limitless. Now, let's get real for a moment. Multiferroics sound amazing, right? Well, like anything worth pursuing, there are challenges. Imagine trying to juggle chainsaws while riding a unicycle. That's the level of complexity we're dealing with. One of the biggest hurdles is finding materials that are both strongly ferroelectric and ferromagnetic at room temperature. It's like trying to find a needle in a haystack. Most materials just don't want to cooperate. Then there's the issue of leakage current. Imagine trying to fill a bathtub with a leaky faucet. It's a constant battle. Some multiferroics have a similar problem, making it difficult to maintain their electric polarization. And let's not forget about stability. Some multiferroics are like delicate snowflakes. They tend to fall apart at higher temperatures, limiting their practical applications. Scientists are a resourceful bunch. They're like master chefs, experimenting with new ingredients and techniques. One approach is to tweak the recipe. By controlling composition and structure, researchers enhance properties. Sometimes a small change makes all the difference. All right, folks, imagine you're a detective at a crime scene. You've got this mysterious material, a multiferroic, and you need to figure out what makes it tick. You need tools, right? Well, scientists have their own set of tools for probing the mysteries of multiferroics. These aren't your average magnifying glasses and fingerprints, though. We're talking about high-tech instruments that can see atoms, map magnetic fields, and reveal the hidden world within these fascinating materials. Think of it like this. Each tool provides a different clue, a piece of the puzzle, that helps us understand how multiferroics work and how we can harness their potential. Section 2, X-ray vision, peering into the structure. One of the most powerful tools in our arsenal is X-ray diffraction, or XRD for short. Now, you've probably heard of X-rays from your trips to the doctor, but did you know they can also reveal the atomic arrangement of materials? It's like shining a flashlight through a crystal and seeing how the light scatters. Different crystal structures produce unique scattering patterns, allowing scientists to determine the precise arrangement of atoms within a multiferroic material. This structural information is crucial for understanding the relationship between a material's structure and its properties. It's like knowing the blueprint of a building before you start making any renovations. Section 3, Neutron Diffraction, Unraveling Magnetic Secrets. Now, if X-rays are like flashlights for atoms, then neutrons are like tiny compasses for magnetic moments. Neutron diffraction is another powerful technique that allows us to study the magnetic ordering within multiferroics. Remember those magnetic moments we talked about? They're like tiny bar magnets within the material. Neutrons, it turns out, also have a magnetic moment, and they interact with these atomic magnets. By analyzing how neutrons scatter off the material, scientists can map out the magnetic structure, revealing whether the moments are aligned in a ferromagnetic, anti-ferromagnetic, or some other complex configuration. Section 1. The Unfolding Narrative of Multiferroics. Concluding our exploration of Magneto-Electric Multiferroics feels like closing a captivating novel. These remarkable materials exhibit more than one ferroic order, revolutionizing technology. The interplay of electricity and magnetism is like a delicate waltz at the atomic level. Magneto-Electric Coupling unlocks unprecedented control over material properties. Despite challenges, the field is abuzz with innovation. Scientists are exploring new materials and synthesis techniques. Section 2. Our Invitation to Explore. The journey of scientific discovery is never truly over. It's a continuous process of exploration, experimentation, and pushing the boundaries of knowledge. And the field of multiferroics is ripe with possibilities, beckoning curious minds to delve deeper. So, whether you're a seasoned scientist or a student taking your first steps into the world of materials, consider this an invitation. Dive into the literature, explore the latest research, and who knows? You might just be the one to unlock the next big breakthrough in multiferroics. The future of technology is being written right now, and multiferroics are poised to play a starring role. Let's explore it together.